Okay, so picture this. It's the turn of the 20th century and the world of physics is in total crisis. The rules that everyone thought were solid, well, they just weren't working anymore. And then this one guy, Albert Einstein, comes along. And he doesn't just tweak the rules, he completely throws out the rulebook and writes a brand new one, forever changing how we see space, time, and gravity itself. Let's get into it. I mean, that's a huge question, right? But the answer is pretty incredible. Einstein basically looked at all the contradictions that were making the smartest people on the planet scratch their heads, and he saw a new path forward. He didn't see problems, he saw clues. And those clues became the foundation for all of modern physics, which eventually paved the way for even crazier ideas, like the search for a theory of everything with string theory. So, to really get what Einstein did, you have to understand the mess he was walking into. Back in the late 19th century, physicists knew that light travels in waves. That was solid. But all the waves they knew about, like sound waves in the air or ripples in a pond, needed stuff to travel through. So the big question was, what's the stuff that light travels through in the total emptiness of space? They came up with this idea of the luminiferous ether. And this wasn't just some passive, invisible goo. They thought the ether was the absolute fixed background of the entire universe. It was the ultimate reference point you could use to measure all motion. A really beautiful, tidy idea, with one giant fatal flaw. Yep, nobody could find the stuff. Scientists built these unbelievably clever experiments, like the super famous Michelson-Morley experiment, specifically designed to detect the Earth moving through this ether. And every single time, they found nothing. Zero. Zilch. This was a catastrophe. It meant that either all their experiments were wrong, or one of the most basic ideas in all of physics was completely bogus. And this is where Einstein's genius just explodes onto the scene. Instead of trying to find a way to save the dying ether theory, he did something way more radical. He just got rid of it. He said, let's start over with two brand new principles and build a new reality from there. Okay, so that first one is pretty straightforward. It just means there's no special stationary spot in the universe. The laws of physics work the same for you whether you're standing still or cruising in a spaceship at a constant speed. So right away, boom, no need for an ether. But the second one, that one is the real mind bender. It means that whether you're running towards a light beam or away from it, it will always pass you at the exact same speed. Our everyday intuition just breaks when you think about it, but this simple idea is the absolute key to understanding the universe. So let's think about that. If the speed of light absolutely cannot change for anyone, what does have to change to make that possible? Well, the answer turns out to be space and time themselves. And this is where things start to get really, really weird and really cool. So let's do a little thought experiment. Imagine you're on a super fast rocket and you shine a flashlight from the floor to a mirror on the ceiling. From your perspective, that light beam travels a short, simple path straight up and straight down. But now, what about your friend watching from the outside as your rocket zips by? For them, that same beam of light travels a much longer, diagonal path. Now here's the kicker. We know the speed of light has to be the same for both of you. So how is that possible? The only way it works, the only way the universe can make sense of this, is if time itself is flexible. For the person watching from the outside, your clock inside the rocket must literally be ticking slower. This is called time dilation. It means time and space aren't separate things. They're fundamentally linked, woven together into the single four-dimensional fabric that we now call the space-time continuum. And out of this incredible unification of space and time comes probably the most famous equation ever written. E equals mc squared wasn't just some random idea Einstein had. It's a direct mathematical result of special relativity. And what it tells us is maybe the most profound thing of all, that mass and energy are really the same thing. They're just different forms of each other, two sides of the very same cosmic coin. Now, special relativity was amazing, but Einstein knew it was incomplete. It only worked for things moving at a constant speed. It didn't account for acceleration, and it didn't account for gravity. So he spent another 10 years working, and he started with another one of those brilliantly simple insights. Take a look at these two scenarios. On one side, you've got a person in a rocket accelerating through deep space. On the other, a person just standing in a room on Earth. Einstein's big idea was that if you were inside a sealed room, there is no experiment you could possibly do to tell the difference between the two. The feeling of acceleration is identical to the feeling of gravity. So he made the leap. What if they're not just identical? What if they're the exact same thing? And that idea completely changed our view of gravity. For hundreds of years, we saw gravity the way Newton did, as this mysterious, invisible force reaching out across space to pull things together. But Einstein showed us that gravity isn't a force at all. What's actually happening is that massive objects, like the sun, are literally bending and warping the fabric of spacetime around them. Planets like Earth aren't being pulled by the sun. They're just moving in the straightest possible line through a curved space. It's geometry. So at this point, Einstein had done it. He'd woven together space, time, energy, mass, and gravity into one beautiful, coherent picture of the universe. But in science, a great answer always leads to an even bigger question. His masterpiece wasn't the end of the story. It was the beginning of a new one. Einstein's theory of general relativity was perfect for explaining gravity. But what about the other fundamental forces, like electromagnetism? Physicists started to wonder, if gravity is just the geometry of space-time, could electromagnetism be a feature of geometry too? Could all the forces of nature be unified under one geometric roof? This led to a wild idea in the 1920s from two physicists, Kaluza and Klein. They asked, what happens if you take Einstein's equations and just add a fifth dimension, a tiny, curled-up dimension too small for us to see? And when they did the math, something incredible happened. Out popped Einstein's original theory for gravity, and as a bonus, the well-known equations for electromagnetism. It was mind-blowing. The theory wasn't perfect, but it planted this powerful idea that would eventually grow into string theory, that the secrets of our universe might be hiding in extra dimensions. And that's really the thought I want to leave you with. Einstein showed us that the reality we experience is just a tiny slice of a much bigger, stranger, and more elegant picture. He opened the door for us to even consider ideas like hidden dimensions. And today, physicists are still walking through that door, following in his footsteps, still trying to read the full rulebook of the universe that he first dared to open.